Well, hello everyone. This week we're going to be doing Chapter 12, actually this weekend next, Chapter 12, and introducing operational amplifiers as our first integrated circuit in our integrated circuits class that we look at. It's going to take up most of the whole course. The entire course is almost about operational amplifiers. We finish up with voltage regulators at the end, but for the next several weeks, we'll be looking at these parts called operational amplifiers. Operational amplifiers are used in virtually all analog circuits, all active analog circuits. Okay, they are, as the name implies, an amplifier. The operational part comes in because they perform mathematical operations, addition, subtraction, multiplication, division, and in fact some calculus too, integration, differentiation, log operations and things like that, depending on what parts you put around them. We'll be going through each one of those mathematical operational amplifiers or math function operational amplifiers in the coming weeks here. But today we're just going to look at the basics of the operational amplifier with no parts around it, just what makes the inside of it work, or what is the basic concepts of it. So here's a schematic symbol of an operational amplifier. It has two inputs, a negative input or an inverting input and a non-inverting input. And then most operational amplifiers have one output. Some of them have two, but for now we're going to just look at the ones with just one output. They also have voltage inputs, a positive voltage and a negative voltage. Most op amps are used in what we call bipolar or dual supply mode, where you have a positive supply like plus 12 volts or plus 15 volts and a minus supply of minus 12 volts or minus 15 volts. There are single-ended power supply or op amps that operate off of a positive voltage and ground. Those are not uncommon. And we talk about those as well. The important thing to remember, we'll go over this again, is that it is an amplifier. How does it? What does it amplify? Well, it amplifies the input to create the output. Well, there's two inputs. Does it amplify one input or the other? No, it amplifies both. Actually, what it does is it amplifies the difference between the inputs. So if this amplifier, let's say, had a gain of 2, all right, and you put 1 volt difference between these two terminals, in other words, 1 volt on the plus and ground on the minus, you would get 2 volts on the output because it's a gain of 2. And what we'll see is these amplifiers, these operational amplifiers in open loop mode, in other words, no parts around them, have gains much higher than 2, more likely 200,000, all right, which is impractical. But because you don't want to, you can't get 200,000 volts out here unless you have 200,000 volt power supply, and if you have that, you better be careful because you're going to get hurt. So don't do that. But we'll see that when we add feedback to this next week, we're going to add some negative feedback to this circuit. You can get some very, very nice practical amplification numbers. Okay, so once again, we have an inverting input and a non-inverting input, and then the power supply, which is plus and minus, and then the output. And this is what I just talked to you about, plus and minus. Here's some pictures of what op amps look like. Here's these look like single or dual at most op amps. Some of the parts will be larger than this and have more than one op amp in them. Okay, so this looks like it's either looks like it's a single op amp. It's only got 8 pins, and this has more. It says 20 pins, a surface mount part, and this one has 8 pins, so that's a single. But surface mount part 20, they could have 2, 3, or even 4 op amps in them, and that's really common. We use those all the time at work because you can get a lot of parts in one small package, especially surface mount packages. There are literally, oh gosh, hundreds of thousands of op amps, parts, different types. Now at the school we use a 741 just for teaching. It's called a 740 LM741 op amp. But if you go on digikey.com and type in op amp, you'll come up with hundreds of thousands of op amps. And why is there so many different kinds? Well, the various parameters that we are about to talk about change as you change the parts. Okay, some of them are faster than others, some of them are high power, some of them are low power, some are used for very special purposes, and so on. For example, instrumentation or audio purposes. So here's an ideal op amp. So I like to pitch this like this. Like if you go to Best Buy and go buy a new stereo, what kind of amplifier do you want? Well, I want a really, really good amplifier because I want it to be really loud, which means I want it to have infinite gain, right? I don't want to have to turn the volume all the way up to hear it really loudly. I want it to be loud all the time. What else? I want it to have infinite bandwidth, meaning I want to hear the lowest of lows and the highest of highs. All right, 20 to 20 isn't good enough. 20 hertz to 20 kilohertz isn't good enough. It has to go 0 to light and beyond. Okay, infinite bandwidth. Infinite input impedance, what does that mean? Well, that's the load that's presented to the source. So if you hook a microphone up to this, I don't want the microphone to even know it's connected, right? Because if the microphone knows it's connected, if it's presented with a heavy load, then the microphone output is going to be decreased, right? Because it has to push that current into a resistor here. So you don't want any input impedance. And the output impedance, that's the ability of the op amp to drive a heavy load. In other words, a speaker. So my speaker might be 8 ohms or 4 ohms. Well, I don't want it to have any problem driving that low impedance. If you have a output impedance here, in other words, a series resistor, voltage is going to get dropped across that, and you're going to get less voltage out. And the next slide, we talk about the practical op amp. It really does have an input impedance, and they really do have output impedance. Now, the input impedance of op amps is usually pretty high. It's in the mega ohms for a particular type of op amp called bipolar op amps, and for FET op amps, field effect transistor-based op amps, it's really, really many mega ohms. Okay, so you're pretty good with that. The output impedance of most op amps is very low. It's less than 100 ohms or even lower. And again, all the different part numbers for op amps, if you go to digikey.com or any parts website, you look at these op amps, their numbers are all over the place, and it depends on what you're using them for. They also have finite gain. All right, they don't have infinite gain. As I said, the 741 has like 200,000, which is a lot. And their bandwidth is limited. It doesn't go all the way up to light, and goes up to the, depending on the op amp, because it could go up to the many tens of kilohertz or hundreds of kilohertz or megahertz, maybe even 100 megahertz. Here's what's inside. Here's a differential amplifier stage. Again, it amplifies the difference between these two terminals. And what does that mean? If you put the same voltage on those two terminals, 1 volt here, 1 volt there, what are you going to get on the output? Nothing. Because they're both at 1 volt. It's called common mode, and we'll see that in a moment. That differential input stage goes to an amplifier stage, and then to the final output stage, which is called a push-pull amplifier, which has a push-pull means it's got a transistor on the top and a transistor on the bottom, a source current transistor, and a sink current transistor. And you might remember some of that from some of your semiconductor class days, 1141. All right, so there's different signal modes that the op amp can operate in. I'm going to refer to this as single-ended mode, where you're only driving one terminal and the other terminal is at ground. Now, this will produce an output, okay, because there's a difference between the two terminals, right? So that's a single-ended mode. This is a differential mode where you're driving both terminals. One with the plus terminal, let's say, of the signal source, and one with the minus terminal. This is typical of a balanced microphone interface. Maybe some of you are familiar with that. Either tip ring sleeve on a 1/4 inch or 1/8 inch connector, or a XLR connector, pins 1, 2, and 3. 2 and 3, I think 2 is the plus, 3 is the minus. on an Excel for some of you audio people. Single-ended mode, you'll see this as just a regular 1/8" jack. Maybe some of your PC microphones are like this. It has just a tip, and then the sleeve is ground. Okay. This differential mode has the advantage of being more immune to noise. Why is that? Because noise normally affects both terminals equally. And remember, the op amp amplifies the difference between those terminals. And therefore the noise, since it's applied to both inputs, or happens that it occurs across both inputs at the same time, it doesn't get shown in the output, doesn't appear. However, on this one, on the single-ended, it doesn't work that way because ground is usually very low impedance, it's really stable. Your noise is going to hit the input terminal, in this case it's the inverting input, and the noise will happen on the output. That's why they use they're called balanced signal interfaces or differential. Some little arrows here. Okay, what I was talking about, that noise, what I mean is common mode operation. It's kind of a funky term, common mode. Basically means the same signal applied to both terminals. So in this case, this particular sketch here, we have the same signal applied to both inputs. You're not going to see anything on the output. Same with this one, same signal applied to both. You're not going to see anything on the output because there's no difference between the two inputs. Okay. Now, practical op amps, these are ideal. Okay, that's what we're talking about here. But practical op amps actually do have a little bit of gain in the common mode operation. In other words, if you apply the same signal to both the inverting and non-inverting inputs, you will see a little bit, okay? But the gain is really down in the dirt. Common mode gain is like just fractions of a dB usually, all right? Very low, or very negative dB, I should say, okay? And again, common mode for unwanted sources, usually just noise, okay, from the atmosphere, from other electrical circuits that are around it. And the result is they're essentially canceled at the output. And the ability of an amp to amplify differential signals and reject the common mode signals is called common mode rejection ratio, or CMRR. And there's a formula for that, AOL over ACM. AOL is the open loop differential gain. And that's that 200,000 I was telling you about, okay, for a 741. Different amplifiers, different parts have different numbers. Some of them are 100,000, some of them are 1,000,000. It depends on what the purpose of the op amp is, what you're using it for. Common mode gain is what I was just mentioning, is how much the amplifier responds or amplifies signals that are the same on both inputs. And we can express it as decibels as 20 log AOL over ACM. Here's an example. 741, there's that 200,000. Typical common mode gain is 6.3. Big difference, right? 6.3 and 200. So we put that 200,000 over 6.3, 20 log at 90 dB. I think it's spec'd 70 dB conservatively, but we're looking at 90 dB, which is pretty good. Okay, there's some parameters associated with each op amp. Maximum output voltage swing is determined by the op amp and the power supply voltages. Some, as I mentioned, some op amps have dual supplies, some have single-ended supplies. Most of the ones we use are dual supply, plus and minus. Also, there's something called a rail-to-rail op amp, where its output can actually get very, very close to those power supplies. Now, the 741, you can, if you put plus or minus 12 volts on it, the most you're going to get out of that op amp, maybe plus or minus 11 volts. So it's about a volt pad, if you will. Some op amps are designed, they're called rail-to-rail op amps, designed to output their outputs operate very close to what we call the rails, or the power supply voltages. So plus or minus 12 volts, you might get 11.9 and minus 11.9 volts or better. Input offset voltage, if you ground both inputs of the op-amp, the inverting and non-inverting output input, you should get nothing on the output, right? Because you're putting in the same voltage on the input, in this case 0 volts, and you should get nothing on the output. Well, it doesn't work that way. There's a slight offset called an offset voltage. It has to do with the imbalance between the currents, imperfect part. And you have to add a little voltage, either positive or negative, between the two inputs in order to cause the output to go 0. That voltage that you apply is called the input offset voltage. And that's a specification, VOS, that's on the data sheet for the op-amp, as is the maximum output voltage swing. But input offset voltage is that input voltage you have to apply in order to make the output 0. Is that important? Yes, sometimes it is, particularly in audio circuits where you're powering on something. You can hear a little pop in the speaker or the headphones. That's that input offset voltage. Okay, you want it to be 0. Input bias current is the imbalance. No, that's the average of the two currents going into the op-amp. So I1 might be the current going into the inverting input. I2 might be the current going into the non-inverting input. It's the average of those two currents. Typically, it's very low. Matter of fact, when we start doing calculations, we assume these are both 0. They're not, but they're so low. Excuse me, they're so low. They're in the very low microamps, and for fed op-amps, they're in the picoamps or nanoamps. They're very small. And then input offset current is the difference between those. And it's this input offset current, actually, excuse me, that causes the input offset voltage. Okay, because if those currents aren't equal, then the input impedance of both of them, which we'll see here in a minute, there's differential input impedance. This one here, if these two currents aren't equal, current going into the inverting and current going into the non-inverting, or if these two input impedances, which is the common mode input impedance, these two are not equal, you're going to get an offset voltage here, right? There's a differential input impedance, which is the measured resistance between between the two inputs. Now, you can't take an ohm meter and just measure these. Okay, you can't do it. It won't give you a valid reading. What you have to do is measure the current going into these and then take a voltage measurement and do Ohm's law. All right, or do a potentiometer where you dial in the value, and when one of the terminals becomes half of the source voltage, you know that the series resistance here in that potentiometer equals this resistance. And we'll look at that in our lab, and you'll understand more about how that works. But for now, just understand you cannot just take an ohm meter and measure these directly. You have to do it indirectly. And then the output impedance is basically its drive capability. How capable is the op-amp of driving current out of it? Because if you start outputting current, what happens? You drop a voltage across this Z out, this output impedance, and you end up with no voltage. Okay, so we want this to be as low as possible, this Z out. One other thing, why is it called Z and not just R? Why isn't it just a resistance? All right, it's shown as a resistance here, okay? But the reason they call it, we're referring to them as an impedance is because what's the difference between an impedance and a resistance? Well, an impedance is basically a frequency-sensitive resistance, right? It has capacitive inductance, it has inductive reactance. I mean capacitive reactance, it has inductive reactance, and it has resistance, all three of those. And the fact is that all of these parameters, all of these input impedance and output impedance parameters are frequency sensitive. They're not just pure resistors. There's some capacitance in here and a little bit of inductance, so they're complex. Fortunately, that doesn't come into play as much as just the frequency response of the amplifier, which again, we look at that towards the end of the course. And the last one we're going to look at today is something called slew rate. Okay, now that's the output of the op amp and its response to a step input voltage. So there's a nice example here. Here's a step input voltage that goes, and it doesn't show the input, but you assume that the input is going immediately up at 0 time here, and then stays a level voltage of 13 volts. So minus 13 to plus 13 is basically what the output is, or the input. It's not clear here in this example, but basically it's a 0 rise time input. What does the output do? Well, it's got this output impedance, so it can't instantaneously produce an output. There's a slope associated with it, and that's called the slew rate. If this slope was 0, in other words 0 times instead of 4 microseconds, it would have to have infinite energy or infinite power. And we know that's not possible usually. So this example shows it going from minus 12 volts to plus 12 volts in 4 microseconds. Now, one thing, normally we do 90% and 10% away from each rail. So this is minus 13 to plus 13. So you'd go 90% of that. They've chosen 12 to 12, which is okay. It's going to be close. Your scope in the lab can measure this automatically, or you can use a graphical method. So we're determining the slew rate for this output, and delta V out is plus 12 to minus 12, so that's 24 volts over 4 microseconds, and we end up with 6 volts per microsecond. That's not so good, but again, different op amps have different capabilities and different specifications in this regard. A high-speed op amp, this number would be in the tens of volts or hundreds of volts per microsecond, whereas a 741 is probably more like a 741. 741 op amp. It's much lower. Okay. Okay, I think that's it for this week. I know it's a lot going over quickly. Please, if you have any questions, post them in the discussion section of our Canvas page, and I'll answer them almost immediately, probably, or very quickly, I promise. Do the homework. And the lab, Lab 12A, we start looking at op amps in your multi-sim. You're going to use that. And good luck. Stay healthy.